This is Agri Challenge Academy, and today's class is on organic chemistry part 1. So, we are going to deal a part of organic chemistry today. Very first, what are the objectives we are going to see today's what are the objectives today we're going to see in our organic chemistry. So in this we are going to reach all these objectives, understanding the reasons for the tetravalence carbons and shape of the organic molecule. So the tetravalency, so we are going to read about this tetravalency and write structures of the organic molecules. We're going to write these structures. We're going to write down all the what are the chemical structures are there, and how we are going to deal with all those structures and everything. And finally, the third one is classifying the organic compounds. So we're going to end up to here organic compounds, and later on we will see the naming of the compounds according to the IUPAC. I know you what is the meaning of IUPAC. You know everyone. IUPAC is nothing but International Union of Pure and Applied Chemistry. The nomenclature derives the structures for the given names. Understand the concept of organic reactions. This is what we are going to understand what are the reaction, what are the different kind of reactions are there, and exploring the influence of electronic displacement on the structure and relativity in organic compounds, and recognizing the type of organic reactions, what are the different organic reactions. We're going to read about that, and finally learn the techniques of purifying the organic reactions. There are many techniques out there, like distillation, fractional distillation. No, there are many things out there, but we're going to deal about those things, and learning the techniques of purifying of organic reactions. So we're going to see about. I think both are same. Yeah, sorry, I'm repeated the point anyway. And write down the chemical reactions, chemical reactions involved in the qualitative analysis of organic compound. At the same time, understanding the principles involved in the quantitative analysis of organic compounds. So like this, we're going to see about all these points. But for today's class, for our convenience, within one day, if we deal with all these things, we will lead to a lot of confusion. But today, we will end up to classification of organic compounds. So we will deal with all these three, and rest all concepts we will cover in the coming classes. Okay, students, we're going to set it, or we're going to learn about the compounds. Very first, what are the definitions? So what is organic chemistry? You want to know what is organic chemistry? So organic chemistry is a subdiscipline. It's a discipline involved in the scientific study of structures, structural properties, reactions of organic compounds and organic materials. That is matter in its various forms containing carbon atoms. So generally organic chemistry means usually mostly we always seen only our study about the carbon compounds. Mostly this is actually, you know what is this structure, this organic structures. This is nothing but it's a chlorophyll structure. For understanding, kept as a chlorophyll structure. So mostly organic chemistry, it's the chemistry of subdiscipline involved in the scientific study of structural properties, reactions of organic compounds and organic material, that is matter in its of various forms and carbon containing. Students, few types of so naturally what we think now, up to now what we have. So whatever the compound have a carbon, so whatever the conditions have a carbon compound, carbon atoms is there, so those are called as the organic compound. We usually think like that, but what happened means in few, especially few compounds like carbides, carbonates are simply oxides of, they also contain carbon, but we can't consider it as an organic compound. We cannot consider it as organic compound. They are the inorganic, they're the oxides of the carbon compound. Even has allotropes of carbon compounds like diamond and graphites are considered as an inorganic compounds. Diamonds and organic graphites also considered as an inorganic compound. But remember, students, they also these so-called carbon compounds, carbonates, also have the so-called carbon compound, but they're not considered as organic chemistry. But what is organic chemistry? For that, we're going to see this. So why to? So what is the need of study of organic chemistry? So each and every compound, our DNA consists of the carbon. Our cotton, naturally, our cotton is also consisting of the carbon, and our petroleum is also one of the organic compound of carbon. And organic matter, yeah, that's one also containing a carbon compound. And our coal, which is very important. It is also an organic compound. So to study about the nature and properties of these particular, especially in organic matter in soil, it contains various forms of organic compounds. So, to know about those organic compounds, to study about those natures, we have to know something about coal. We have to know something called knowledge called organic chemistry. We want to read about something called organic chemistry. So for that, we are going to see some historical background of the organic chemistry. So science of organic chemistry is about 200 years old. How many years old? It's almost, it is a, we know about the science around 200 years ago, but around in 1870, chemists began to distinguish two parts. So, but in 1780, what everyone is thinking, organic compounds obtained from plants and animals. This is what you usually have idea in those days, when in 1780. And inorganic compounds are mostly from mineral sources. This is usually the idea what we know. So, what is a broad idea in previous historical background of organic chemistry? Organic compounds derived from the plant and animals are called the organic compounds, and compounds are prepared by the mineral sources are called the inorganic compound. This is an idea having those days when and during 1780. But the Berzelius, there is another famous Swedish chemist, proposed that vital forces were responsible for the formation of these organic compounds. So given this important concept called vital forces, which is a very important, the vital forces is all the climatic forces, etc. Are the different forces are responsible for the formation of this organic compound. This notation was rejected, but however, after after this Berzelius proposal in 1828, when F. Holler synthesized an organic compound, so called urea, urea, our fertilizer, urea from inorganic compound called ammonium cyanide in a lab. So this is called ammonium cyanide. NH4 CnW gives rise to NH2CO NH2. This is called the urea. So overall, by seeing all these conditions, you know, so up to so this person, this F Holder, have completely disproved this above theory, the vital forces, and also he disproved that organic compounds derived only from plants. That is also has been disproved. But this person, this Holder, have synthesized a inorganic compound urea from this ammonium cyanide. So synthesis of acetic and also further discoveries of synthesis of acetic acid, cobalt, and that of methane by the Breathtoll confirmed that organic compounds could be synthesized from inorganic sources in the lab. So overall, students, so up to now, what before 1780, what everyone think that organic compounds are the plant products or animal products have been decoded. But later, even Berzelius also said that some vital forces are involved in the synthesis of the formation. But what happened all of a sudden? The notation was rejected in 1828 when F. Holler synthesized an organic compound, urea, from inorganic compound called ammonium cyanide in the lab. So from ammonium cyanide, this Holler had prepared an urea. At the same time, Goebel prepared an acetic acid, and Brent, Brentlot. I'm sorry, please forgive me. I'm unable to utter this word. Brentlot. So this person had proposed, has been prepared a methane, and after all these reactions, what finally we came to conclude, these organic compounds could be synthesized from inorganic labs also, which ultimately disproves this above theory. Now let us see in the next slide what we are going to discuss. So sources of the organic compounds. So okay students, now we will get an idea. So organic compounds are not only derived from the plant and animal products, but also from mineral compounds also. From mineral compounds, so previously in 17th or to a in 17th century, 17th hundreds, what everyone thinks that it is so organic compounds only derived from the animal and plant sources, but later it was disproved by the many scientists by synthesizing the acetic acid, methane, and other organic compounds. But okay, that's a clear picture. That is sort of small historical background. Let us come to the sources of organic compounds. So what are the sources? Those are called the major source of plants. Plants as a major source for the organic compounds, heavy source of organic compounds, and animals, our animals, maybe any animal, it's another source of organic compounds. And a coal is another source of organic compound. And a petroleum is a vast source of organic compounds. So from these are the different sources, or different parts we can get the organic compounds. See students, these plants and animals, also providing some organic compound. At the same time, these mineral compounds also giving some organic compounds like coal and petroleum. So this is the difference. These are the major source of the organic compounds. So let us see the classification. So overall we get some distinguish the historical background of organic chemistry. Now let us see some classification of organic chemistry. What are this? So organic compound, students, remember there are two compounds are there. One is called the aliphatic and cyclic compounds. Aliphatic and cyclic compounds. So in this we can see only straight chain compounds. So carbon, 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 like this it will be. Only straight chain compound. In cyclic compounds, we can see some cyclic compounds like benzene and other cyclic compounds will be this. And further, the cyclic compounds again have been uh, classified into heterocyclic compounds, which contain heterocyclic compounds and homocyclic compounds. And later on, this alicyclic and heterocyclic and alicyclic, and these heterocyclic compounds were again divided into alicyclic and aromatic, and this aromatic, and these homocyclic compounds also have been derived into alicyclic and aromatic, right, students? And this aromatic compounds also we can see benzenoid and non-benzenoid compounds have been so called, have been classified. 1 minute, students, I will check whether whether I am confusing whether it's benzenoid compounds are homocyclic or heterocyclic. uh, so like this we're going to deal many things in chemistry. 1 minute, students, 1 minute. Compounds were again divided into alicyclic and aromatic, and homocyclic compounds were again divided into alicyclic and aromatic. And this in heterocyclic aromatic compounds were again divided into benzenoid and non-benzenoid. Benzenoid means nothing but the content which consists having a benzene ring, and here in this we cannot see any benzene ring. So like this we can see different compounds. And this aromatic compound, students, aroma means it is a smell. We get a good smell. That's why it is called as a aromatic compound. So aromatic, it is called as an aromatic compounds. So overall this is the clear picture. Before with this classification is very important, because based on this classification only we are going to read many things and we are going to identify the organic compounds. Okay, students? So overall there are two types of two compounds will be there in major in organic compound. One is called the aliphatic compounds and the cyclic compounds. In cyclic compounds we can say heterocyclic compounds and homocyclic compounds. Again, in homocyclic, both in hetero and homocyclic, they were divided into alicyclic and aromatic. Here also in homocyclic also they have divided into alicyclic and homocyclic. And coming to the heterocyclic compounds in aromatic, we can see benzenoid and non-benzenoid. So this is a clear picture of your classification. So this is your clear picture classification of your organic compounds. Let us see now. Let us see another section. So tetracovalency. So students, actually, carbon has a one special character called character. What is that called? Catenation capacity. What is a catenation capacity? What is the meaning of catenation capacity? Any idea? Do you have any idea, students? What is the meaning of catenation capacity? Catenation. Any idea? Do you have any idea what is the meaning of catenation? Yes, any idea? If anybody have any idea, you can say what is the catenation capacity of carbon. Please, I'm not. It is not audible. Can you repeat once again? Sense of carbon. So before actually carbon, we immediately organic compounds we're going to deal about only carbon compounds. So carbon compounds are carbon compounds in a sense which is derived from both plants and animals, and mineral compound also. But overall, students, remember there is a special character for carbon called catenation. That means it can bond with four atoms or four carbons at a time. It can form four bonds at a time. That is called the catenation capacity. But remember, is it possible? But there is only two lone pair electrons are there. So to avoid this, so to avoid this, what happens? There will be some exciting state will be there. So what is excited state? So before that, remember atomic number of a carbon is 6. So this is the electronic configuration 1s2 2s2 2p3. So this is a normal stage. What is there in first orbital? It's have a two electrons. Two electrons has been first two orbital has been satisfied. But coming to the p orbital, it is an x, y, z. So 1 1 0. No problem. But the in excited state, when the energy was excited, what happens? one electron from the one s orbital is jumped from 2s to again z. So now how many lone pair of electrons are there? There are the four lone pair of electrons are there. So to satisfy the charge, or to satisfy this valency, this four electron valency, what we have to do to get that octet configuration, octet configuration, everyone knows we need an 8 electrons in an external shells of external electronic cloud of any atom. So there are four electrons are there. To attain stability, there are three options are there. So anyhow, after excited, when the carbon was excited, what happens? One electron was came and jumped into the 2pz. So there are the four lone pair electrons are there, right? So to attain the stability, there are the three chances are there for the carbon. What are those? Either you should gain four electrons, you should get the four electrons, or it should lose four electrons to attain. That means it will be left out with only two electrons, though then the stability will be, or it will go for sharing. So overall, students, if you remember, gaining four or losing four, we need a lot of energy to achieve these two, or to these two targets is very difficult. But at the same time, if we started sharing, if we started sharing electrons, if we started sharing electrons, you know uh, if we started sharing of electrons, it will be very easy. So no need of that much energy, and it is very convenienceable, it is very convenient and very easy then compare with gaining or losing of electron. That's why in organic chemistry we can see mostly there is the sharing of electrons will be taking place between the functional group. What is functional group? We will see all these things in the coming classes. Let us see, this is the overall picture of tetra covalency of, this is the tetra covalence of the carbon atom. So this is the students overall picture. There's the carbon number of atomic number is 6. The one, this is the electronic configuration, 1s2, 2s2, and 2p. Same time in normal state is 1s2, 2s2, 2px, and 2py, 2pz. So excited state is 1s2, 2s2, 2px, and 2py, and 2pz. There totally there is a four lone pair electrons are there. That is there to attain stability. We will share the electrons between other atoms. So let us see what happening in next. So before that, you have to know the hybridization. So there are the three types of hybridations are there. So sp2, sp3. So or you can come sp3 hybridization, sp2 hybridization, sp hybridization. So what is this hybridization? So you will see now we are going to see about this hybridization. There is a pi bond, sigma bond, many things we are going to deal about all those things. Now let us see. Very first we will see the sp3 hybridization, which mostly happens in methane carbon. So sp3 hybridization means, remember student, there is an involvement of this thing. So this is a carbon ground state. So there is a two lone pair electrons, but when excited, what happens? This is 1s2, this is 1s2, this is 2s2, this is 2py, 2pz, this is z, xyz. This is x, this is y, this is z. So what happens? One electron from 1s orbital, this is s2 orbital, will jump from here to here. So now we get. So what happened? Carbon hybridization will take in place. So the hybridization is one type of bonding. So this bonding will be taking place. So here you can see there is a mixing of one s orbital and three p orbital. So what happens? It leads to the formation of sp3 hybridization. So overall, there is a mixing of sp3 hybridization. So methane molecule, what will happen? This carbon four electrons of carbon will join and form the carbon atom. Now this is the compound, students. See, this is the sp3 orbital. This is one s orbital of this. So one, two, three. So there are three sp3 orbitals will be there. Four sp3. This is three up here, and backside there is one more three. What will happen? These lone pair electrons will be joined by the hydrogens. So this leads to the hybridization. So this leads to the hybridization. This is called the sp3 hybridization. sp3 hybridization, there is an involvement of one sp and xyz orbitals, two p orbitals. So this involves, so one sp, one s orbital, and two p orbitals will be involved. So what will happen? Automatically leads to the sp3 hybridization. So methane is the best example for a sp3 hybridization. So hybridization this is the cause for the hybridization. So valence of sp2 hybridization. Sp2 hybridization, this is happens in with ethane. In ethane compounds we can see. So here what will happen, mean this is the ground state. If you knows what is the ground state, excited state automatically will happen. But here what happens, only one or three electrons will come into pair. Only three electrons. In previously we can see three xyz. So x y sp spy sp spx spxyz. So spx spy spz orbitals were involved. So this is x, you know all these things, x, y, and z. You should know these are all the very basic principles which you have learned in your in your plus 2 syllabus. So what will happen, one electron will jump here, but in a sp2 hybridization there is involvement of these three electrons. So this leads to the formation of sp2 hybridization. So in this sp2 hybridization we can see two pi bonds will be taking place and one sigma bond will be taking place, and rest all these two hybrid compounds will form a bonding with hydrogen. So this leads to the sp2 hybridization ethane. This is called the carbon atom hybridization state. So this one electron is called unhybridized. There is no hybridization will be taken place. This is regarding the sp2 hybridization. So in sp2 hybridization we can see two pi bonds and one sigma bond. And sp hybridization, nothing will be there, only two things will be there. See the reduction. So very first we can see we can see four electrons were involved, but here later it is three and now it is two. So here also you can see there is only two one sp one s one p orbital were involved, and this leads to the formation of our sp hybridization. Mostly we can see this type of ethylene ethine, sorry, not ethine compounds. Especially in ethine compounds we can see this sp hybridization. So you should be very clear about this sigma bond and pi bonding and sp hybridization, which is very will plays a major key role in our valency bonding theory. So what is pi bond, students? So this is very fundamental approach. Actually, you should learn in your plus two itself. So the p orbital are mutually parallel and perpendicular to the plane, right? You should know all these structure, students. If you ask me what is p orbital, I'm sorry I can't help you, because you're a MSc student, so you should know all these things. So this the structure of p orbitals. You should know what is the structure of p orbital, s orbital, sp, y, x, y, z. We should know all these things. So the rotation of carbon-carbon double bond is restricted. We can't rotate the we cannot rotate the double bond very easily, but we can rotate the single bond very easily. We will learn how why the only double bond cannot be rotated, but only single bond is rotated. You can see all I will say in coming classes. So rotation about the carbon-carbon double bond is restricted. Double bond is very restricted, but electron charge cloud of the pi bond is located above and below the plane. See, this is the above and below both side. You can see that clouding is there. This results in electron being available at the attacking region. So what happens, electrons is, so electronic cloud were present in this region only. So in this region parallel to each other. So naturally almost all the attacking all the bonding or everything will be taking place in these conditions only, this rotation conditions only. Actually pi bonding, this is a pi bonding, especially in chemical bonding chapter. Usually you have to know about all these things. So this is regarding the pi bonding. Coming to the representation, so how we are going to represent our organic compounds? There are four ways in representation. One is complete structure, like this, or condensed structural formula, or we have to go with this formula, or bond line structure, like this bond line. This is like all these things. If I'm not wrong, in your MSET exam, especially in Andhra Pradesh MSET exam and your intermediate exam, you may have written one structure for 1 or 2 marks. And coming to the last one is 3D dimensional representation, which is usually we see in our internet. Now let us see complete structure formula. This is called the complete structure formula. You can see ETH, and you should know all these things, students. Meth, ETH, pro, but, pent, hex, hep, non, duct, oct. You should know all these things. I will anyhow I'm going to teach. But complete structure formula, it is called ethane. It is called the complete structure. You can represent an ethene, which is double bond. If it is double bond, we have to represent as ethene, and the triple bond is ine. And if we have any functional group called OH, as alcohol group, it is called OR. So this is a complete structural formula. And condensed structure formula, we can see ethane and ethene and ethyne. See, both the difference is that here we have here in this representation we have written the complete structure, but in down we have written only stuff formulas. We just ignore all these lines and everything. Just we put a just we just simply we put a formula, structure formula. And coming to the bond line structure, students, is nothing but just we simply ignoring. So instead of that, we just draw. So each dot is considered as a carbon atom. This is one carbon atom. This is one carbon atom. Or this is one carbon atom. Or simply, if there is any other compound, we'll just write its names, right? So this is just it's a line representation. Just the dots we will consider the dots, we consider it has a each one has one carbon. This is called the bond line structure formula. And another one is bond line structure formula continues. So if you are just a few more examples are this is a normal representation, our regular structural representation, but this is a bond line representation. See, this is a bond line represent this part is here, is represented in bond. So each dotted line is considered as the carbon. This is one carbon, this is one carbon, this is one carbon. Cyclohexane, our cyclohexane, see, each one is one carbon. So in this here, each one dot is considered as one. I will take another color. So each one is considered as a, here one carbon, here one carbon, here one carbon, here one carbon, here one carbon. So we are only represented through only lines. And butanol also, students, and butanol also we have representing in a line formula. This is one type of structural formula. This is a normal representation, it's a bond line representation. These are the different type of representing our organic compounds. Now let us see another thing, that three dimensional. This is three dimensional. We usually see the dimensional way. This is a outward wedge, is outer wedge. This because this is now towards us, but this is a back side. It's called the inner wedge. This is called the inner wedge. Inner wedge is called the outer wedge. So these are the three-dimensional representation of our organic compound. This is a methane is our three-dimensional representation of organic compound. And coming to the aromatic compounds, so these are the representation. Coming to the aromatic compound, students, we will read about all these things, but before, let us see what is aromatic compound. So aromatic compounds are the chemical compound that contains conjugated pair of ring systems. See, conjugated pair of ring systems which delocalized pi electronic cloud. See, there is electronic cloud here. This I'm represented here. Actually, this is the original structure. This is delocalized. We have an electronic cloud. Pi electronic cloud. Electrons are free to cycle around in a circular arrangements of atoms that are alternately single and double bonded to one another, contributed to the atoms arranged in a ring form. So in aromatic, generally aromatics are nothing but they are ring structures. They have a ring structure and they have a pi electronic clouds. So the number of pi declosed electrons are represent is be calculated way, or we can represent in 4n plus 2, whereas n we can say at 0, 1, 2, 3, and so on. This is known as the Huckel's rule. We will read all these Huckel's rule etc. in coming classes. Example: our benzene in a 3 pi, there are 3 pi bonds are there and 6 electrons are there. Also aromatic compounds have some aroma. There is a good smell is there. So this is the ring structure is called the aromatic structures. This is a repetition, students. It's a classification of organic compounds which we deal each and every compound. In coming classes we are going to deal each and every compounds. And these are the aliphatic compounds. These are the compounds that the aliphatics are nothing but aliphatic compounds are nothing but the straight branch chained compounds. As I said, these are the straight branch chained compound. There is no closed rings. Simply examples are ethane, isobutane, acetic acid, and aldehydes. So aliphatic compounds are the straight chained compounds. Remember, aliphatic means straight chained compounds. Coming to cyclic compound is nothing but your cycles. You have a closed rings like furan, thiophane, pyridine, pyrene, thionine, piperazine, pymeridine, thiazine, oxazine. You will read about all these things. Cyclic compounds are nothing but called they're the cycle compound. Cycle compound, homocyclic compounds, ring compound is only carbon atoms. Here you can see only carbon atoms. In this cyclic compounds, you can see only carbon atoms. We can see only carbon atoms, students. Nothing is there. Other than that, we can see nothing. Only carbon atoms is there. There is no other compounds will there. See, if there any oxygen, if there is oxygen, that is not called as a homocyclic compound. That is different. So it is the cyclic compound in cyclic compound. Homocyclic, homo means simple, only one compound. Only carbon compound will be present. Coming to cyclic in homocyclic, alicyclic means in homocyclic itself there is a two compound alicyclic. So rings composite carbon atoms only. So also chemical compound resembles the aliphatic compounds, but in alicyclic we can see these alicyclic properties are somewhat resembles to our aliphatic compound, the straight chained compounds. Though it is a cyclic compound, some characters will completely resembles to our aliphatic compounds. So in coming to the homocyclic aromatic compound, the ring compound consists of carbon atoms only. They have aroma and also consist delocalized pi electrons are there. That means they have some benzene compounds also will be there, like cyclopropane, cyclohexane, cyclohexane, cyclobutane. All these things will be present. And coming to the benzenoid rings, an aromatic in benzenoid rings means nothing but it has some benzene rings, alanine, everything. A non-benzenoid means paka opposite. In aromatic, if it is non-benzenoid, there is no benzene. Instead of benzene ring, there will be other type of rings are there. We will read all these things in next class. Cyclic in heterocyclic alicyclic compound means it's also consists with the carbon compound. It also have a other compound like oxygen. Here there is a nitrogen. Here there is a sulfur. There is oxygen. Methane is there. So all these compounds. So other than compound, there is any other compounds also there means rings are composed of atoms other than carbon also is called as alicyclic compound. Heterocyclic is called the alicyclic compound. You should remember. And coming to heterocyclic and aromatic compounds means these have both aroma and also consider delocalized pi electrons. Which have some like furan and thiophene and pyridine. Functional group means functional group is nothing but uh, actually I think 1 minute students. So functional group is nothing but it has very special characteristics are there. I think I will stop up to here, and tomorrow maybe I will plan for another class. We will continue about this functional group and everything in coming class. Thank you very much, and you can leave the class now.